Well, thank you very much, everyone. Thank you to all the organizers. It's a pleasure to be here. So I'm going to, I need to start with a confession. I don't know how to pronounce the name of my own talk. so this guy here is supposed to be called Theseus. So I'm going to butcher the name all the talk. So if you actually know how this is pronounced, I'm very sorry. Yeah, I'm going to go with Theseus. I tried to do Google Translate for a long time to just catch it, but I'm going to do my best. Cool. So, well, I'm Pablo Galindo. I'm from the Python core team. I'm also in the Python Steering Council, and I'm the release manager of 3.10 and 3.11. And here, so this talk is going to be an interesting talk. The idea of this talk is to show you like a little puzzle. And the puzzle is basically going to be about like what is really Python. And not only what is really Python, but like what makes Python Python. And for that, we are going to basically go a small journey that starts with the real thing that this sentence is representing, which is the ship of Theseus, which again, I don't know how to pronounce. This has a long story about it, but if you have ever seen slides like this with a lot of text, this is a mistake. Like, never do this. So let's remove all this text. I'm going to just, you want to listen to me, right? So, okay. So the story goes as follows. So there is this person called Theseus, right? And this is the guy who slaughtered the Minotaur in Greece, right? There's this labyrinth, and then he goes there, he does a bunch of things with a bunch of thread and whatnot, and kills the beast. Nice. The guy is famous now. Don't do this to be famous, not recommended. But then the thing is that this guy goes home, right? And he goes in this big ship. And then when they arrive there, because the guy is famous, then everything this person is touching is also famous. So the ship is now famous, right? So they say, wow, let's have this ship here. This is fantastic. But as time passes, the ship deteriorates, right? So now they need to change some parts of the ship. And the first year, they change the bottom of the ship, and as time passes, maybe the upper part of the ship also deteriorates, so they need to change it as well, right? So after like let's say 80 years, what it remains of the ship is nothing from the original version of the ship, right? Because you have been changing all the ship. And then the question is, this is a philosophical question: is the same ship? Because people still probably, have it displayed there, very beautiful, and they say, this is the ship of Theseus, right? But, some small person may say, like, yeah, but like, no, not really, because you changed all the ship. Like, no, there is nothing remaining from the original one. Is it still the same ship or not? In the same way, this question, there is no real answer. Like all the philosophy questions, they are traps. There are no real answers. It's just for you to think and like for philosophy teachers to have a salary. In any case, the important part of this talk is like the ship is going to be Python, right? Like, and the question is like, if this is the language after like, let's say this is the language in version 3.6, with F strings and whatnot, and after a bunch of times, we change everything, and now is this other language, which is Python 3.12. And the question is the same language, right? The same way we change a lot of things. We added a bunch of new things, so this is even more complicated because we added stuff. Now our ship does like interdimensional travel and whatnot. So now is the same ship or not? So this is the question we're going to explore, right, in this talk. There is many ways to go around like trying to understand this problem. One of the things that you can do is like looking literally at the same question, like, okay, so how much of the original ship is still there, right? So what makes a programming language? Well, it's the code that the programming language is into. We are going to see that this is not everything, but let's look at it. So this plot here, what it shows is the amount of code that remains over time. So for instance, this part over here, this blue part that goes up and up and up, is the original code that Guido and Rose wrote in 1992, right? And as you can see, this code, there is still, like if we go to 2023, so today, there is still some code that he wrote that is still on the repository, but most of it, which is the area that is in blue, has disappeared. And this is code that was added in 2002 that basically now remains very little, and so on and so forth. So as you can see, first, we know two things. If you look at today, which is the right part of the plot, there is a lot of code for a lot of years still in the repo. This means that, Python today is not like Python at the beginning, which is only made by one person. Python today is made by many, many persons. This is not people, this is just years. We are going to see people in a second. But like, as you can see, like, there is a lot of old code that still remains, right? Like, even code from the start. Obviously, as you can imagine, like, older code tends to remain less because, we need to update it, and because seg faults and, it's all C code and nobody likes that. But at the end of the day, what you can see is that at the end, the picture is not like, it's just one single thing. It's made of many, many things. So if this was the ship of Theseus, we have changed quite a lot, right? And like changes that were made in previous year, they still remain there, even if very little. So that informs us that, this situation is quite complicated. Another plot that you can see is this one. With this shows you basically contributions by people. So these are the most prolific contributors, and what this plot shows you is how much of the code is in the code base. So for this plot here is Guido, and as you can see, like, as more people started to contribute, the percentage of code that Guido wrote is less and less and less, and other contributors start to rise, right? But an interesting aspect of this is that even if these are the most, like, prolific contributors, if you look at today, the percentage that every one of them, that all the code that they contribute in the code base is very small, which means that, if the most prolific contributors have a very small amount of code in the final, code base, it means, like, the conclusion is that there is a lot of contributors, right, that are not being shown here, right? So this is the second thing that we can see. Like, Python is not only made from, code from a lot of years, it's made by a lot of people, like a lot, right? And therefore, what you are dealing here is it's a very complicated ship, right? It's a ship made of a lot of different people, a lot of visions, a lot of code, right? So that's the second thing. Like, how can we ensure, and this is a problem you can imagine, because if you want, like, the perfect language, like Python, right? Normally, these things are made with a vision, right? Like, if there is someone who has a vision, in this case, it was Guido at the beginning, you can say, well, this is what Python is going to be, and, I have it, he's here, it's perfect, and people will follow it. But this is not what is happening. Like, the language is basically made from all the people and the community, right? So the question now is, how do you ensure that when you have this many people contributed to the language, this doesn't transform itself into something totally different, like, I don't know, C++ or something like that, right? Nobody likes that. And you can plot this thing in many ways. So this is, for instance, this other plot shows you, like, the line of what is the chances that if you commit code today, this code will survive in this many years. So for instance, if you commit code today, the chances that it survives today is 100%. Okay, that makes sense. Philosophy. But after, like, 1, 2, 3, 4, 5, 6 years, the chances are, like, around 50%. So, like, after 6 years, the chances that your code is still in the code base is 50%, which is quite a lot. It gives you, like, the half time, right? Because, surprise, my background is physics, so I like to say physics things. And this is a perfect segue to the next thing that I want to show you, which is that the question that, what makes Python is more complicated because it depends on you. Let's go with this. So this is the color pink, right? So what is interesting about the color pink? Well, what is interesting about this color is that it doesn't exist. Okay, what do you mean, Pablo? Like, it's here, like, I can see it. Well, it turns out that, what is color, right? Let's think about it for a second. So light is made of photons, right? And these are these wave packets, and they have a frequency, right? And the faster the frequency is, the more the color goes to blue. So if it's very slow, it's red, and when it's very fast, it's blue. And when these photons reach your eye generates electrical signals that go to your brain, and your brain interprets those electrical signals as color, right? And then, you have photons of different vibrations that corresponds to different colors. So for instance, 400 nanometers is blue or something like that, and 300 I think is red or something. Turns out that there is not a single frequency that is associated with the color pink, which means that there is not a single photon that is pink. And you will say, so how I'm seeing this? Well, it turns out that the color pink, like, if there are no photons that are pink, the only way to produce this sensation in your brain is having white light that has green remove. So you cannot have just one single photon reaching your eye and producing the color pink. You need a lot of different photons at the same time, so it's basically white light minus green, and only when that happens, your brain interprets that many photons as a new color. It only happens with this one, which is pink, which means that pink only exists in your brain. Like, there is nothing physical about pink. There is no photon that is pink. It's a sensation that your brain created. But as you can imagine, like before I told you, you could say that this is just another color, but it's a very weird color. It's a color that only exists in your brain, right? Like if you look at if you ever, like, I'm not lying to you, you look at one of these like diagrams that shows you like the spectrum of visible light, so this is the vibration associated with photons, there is no pink here, right? There is like very violet, but no pink. Pink will be like on this side over here, but because there is no pink, you will need to like bend this diagram. What I'm trying to say with this? Well, what I'm trying to say with this is that you need to be aware that things that you normally think that they are very normal and you're used to them, they may be like very complicated, and in particular, they may be very dependent on you. And the same way pink doesn't exist and only exists in your brain, surprise, Python really doesn't exist. It just exists in your brain. We are going to see why in a second, but this is very important because if you are in charge of thinking, how do I ensure that this language remains the same when I'm making change to it, right? Like this is a question that in the core team we make all the time. Like if we are deciding to add like a new grammar feature to Python, we need to decide if this is a good idea or a bad idea. And one of the questions that appear quite a lot is that if we add this, it's going to be good, but also like is this Pythonic, right? Like is people going to still think that this is Python, or is this new feature that people are not going to like? And this question is very hard to answer if Python is something that depends on every individual person, right? Like the Python that this gentleman over there is seeing is not the same thing as the Python that some person over here is seeing, right? So that makes the whole thing even more complicated because it's something that depends on the observer. And this basically like lead us to some way to try to formalize this in some framework, right? So for that, we need to go a bit deeper and think about like what defines Python, right? Because if this is something that only exists in people's mind, we need some frame of reference because otherwise, everyone will have a different answer here. And what basically the most core thing that defines the language is the Python grammar. And this is going to show basically why Python is something that only exists in your mind. So for instance, this code, is this Python? I will leave you like 5 seconds. I will not ask you to raise hands because that never goes well. But like, just look at it. It looks kind of weird, right? It looks funky, like there is some templates there. It looks like C++. Well, it turns out that this is just valid Python. Like if you parse it, this is the AST. So this is Python. Like, if you look at this is just like the matrix multiplication. This is like less than and bigger than. This is unpacking. So this is a annotation. This is just a variable name called auto. So no, this is Python, and you will look at it and say like, this is not the Python I know, right? This is something weird. Like, it's not my thing. But this is a valid thing, right? Like if you go to the specification, the interpreter reads this and says, yeah, this is as valid as your code, which is kind of weird, right? Because like then what is real, right? Like what is real? What is our language? For answering that, I'm going to show you a small story that is going to show you how this plays into the story of how Python is made. So this gentleman over the left, the one on the right is myself, but this gentleman on the left is my friend Gukesh Langa. So he's the release manager of Python 3.8 and 3.9, and now he's the Python core developer in residence. So it's this person that is hired by the PSF to, he's also a core developer, but he's hired by the PSF to help with the maintenance of CPython. And an interesting story about like Gukesh is that in the year 2018, he invited me to the Facebook office, right? Like, in London, which is like this fantastic place. There is like a barista. I don't work at Facebook, but I work at Bloomberg, which is also a big company. And I said to him, well, I'm not going to be impressed by your shenanigans, right? Like, I also have a big office. But when I went there, they had a barista, which I don't have at Bloomberg, and I was like, wow, this is the next big thing. And when I was there, we had lunch, and in that lunch happened a conversation between us that actually changed Python forever. But before talking about what we talk in that particular conversation, I need to introduce you a bunch of concepts before about like how to read grammars, because this conversation is going to be about grammars. So if you ever like guess where is there any place when we have like a document that says what is Python? The answer is yes. It's the grammar. The grammar tells you like what programs are valid and what programs are not valid, right? Like when you write something invalid and says syntax error, so there is this file that tells you like what is a syntax error and what is not. And this is a file in the repo. If you go there, it's in grammar/python.gram. And now it's a bit different, and it used to be a bit simpler before. So, but for basically explaining how to read this file, I'm going to use the simpler version. So if you go to this file, you will find things like this, which are called rules. So rules are basically things that are valid, right? And they have a name. name, so normally on the left, and they have a description, which is the actual rule on the right. And you can have alternatives. So for instance, in this particular case, I have the same rule name with 2 different descriptions. This basically means that this rule can be either the one on the top or the one on the bottom, right? Either, right? Sometimes people don't write this because they don't like to write 2 things, so they use this pipe operator to say or, right? So this rule is either this one or this one, right? Cool. Okay, but then what you can put there in the descriptions. So for instance, they look very similar to regular expressions. So for instance, in this case, I'm saying that this rule name is the letter A in uppercase 1 or more times, right? So, okay, so 1A matches, 2A's also matches, 0A's doesn't match. You can have also like the asterisk, which means 0 or more, like regular expressions, so very simple as well. But you can have something more complicated. For instance, you can have these square brackets that is an optional part. So this rule is the letter A optionally followed by something else. And for instance, you can combine them to do something like this. Like this is a rule for that describes all the grammar file itself, which is just the ones that I enumerated. So you can even describe the language of grammars in a grammar, right? Which is kind of cool. It's called the meta grammar and makes people's heads explode. But okay, but if you go to the actual file, you will find something like this. Okay, let's try to make sense of this. So if you go to the top, you will say, okay, so a file in Python is a new line followed by 0 or more statements. And you say, okay, what is a statement? So you go to a statement and say, okay, a statement is either a simple statement or a component statement. Well, we still don't know what that is. Let's follow. And you go to component statement, you start seeing things that you probably recognize, like if statement, while statement, for statement, try statement. And if you go to those, you will start seeing things that make sense. So for instance, if I go to, I don't know, for instance, the if statement, you see that if statement is the expression if followed by something, followed by a column, followed by something called a should, and maybe you don't recognize the whole thing, but you start seeing how this is described, right? How this makes sense. So this is the grammar itself. And just some terminology for following the story. If you see the words between quotes, that's called a terminal. It means that is the word that I'm expecting. Like when I say while, it's just while, the word while. If you don't give me the word while, it doesn't work. And when you see these white parts that have names, this is called non-terminals. This means that this is another rule that I need to go there and find what it's doing, right? So this is the 2 things. Cool. Just some extra things. So before Python 3.9, we used to have, actually this is very interesting, we used to be the only major language on the planet, major language as like the 20 biggest language in the TOB index or something like that. Just, define yourself what bigger language is. I'm not a philosopher. So we used to be the only big language that have an LL1 grammar. And LL1 grammars are quite interesting because these grammars are one of the most simple grammars that you can ever write, right? Like if you're writing a parser and you're learning how to do parsers, this is the first thing that people teach to you because they are super simple to write and super simple to parse. And LL1 grammars basically are grammars that you read left to right, so that's the first L. You do something called leftmost derivation. This means that when you are making sense of the grammar, you start expanding those non-terminals from the left. And this is the most important part of L1 grammars, is that when you are making sense of the text, you can only look one word ahead to know if it's 1 or 2. So for instance, if you're trying to distinguish if you are reading a for statement or an if statement, you are only allowed to look at the next word. So if the next word is if, then it's an if statement. If the next word is for, it's a for statement. Well, in this case, it's simple, but you can imagine that maybe there is some rule when you may need to pick a bit more just to ensure that you know what it is, right? But in this case, you can only do one token ahead. And this makes the grammar not only super simple to write, but super simple to parse. And this is one of the most important parts that makes Python Python, and even said by Guido himself, which is that if it's very easy to parse by the machine, it's very easy to parse by a human. And this is very important because when you're reading code, it's very important that you are, when you're reading it, you can make sense of what you're reading very fast. And this doesn't happen in other languages. For instance, let's say C++. I'm sorry, like I'm picking up this language, but like there are also other bad languages. No, I'm joking. All languages are good. So the idea here is that if you're reading and the language doesn't have this property, it means that you need to keep a lot of state in your head to make sense of what you're reading, right? Is this word a type or is it just a variable name, right? So you need to remember a lot of things when you're reading to ensure that you understand what when you're reading. But if the language only has these properties that if you just know the next word, you can immediately know what you're reading. That's very good for humans and for machines, right? So for instance, this is a bunch of the grammar of Python. We are not going into detail. But the other thing that is is important is that if you are only allowed to look at the next word, then a very interesting property that you may be interested on is that, for instance, let's go to this flow statement in the middle. It can be either a break, a continue, a return, a raise, or a yield. So if I'm only allowed to look at the next word, I know that if I know the next word all of these things can start with, I can know immediately if a sentence that you gave me or a bunch of like words is one of these or not. Because if the sentence starts with one of the words these different statements can start with, then it's good, like it's valid. If not, it's bad. So that is called the first sets. So for instance, if you look at the first sets, this is the words that the statements can start with. Well, some of them make sense, right? Like print statements can only start with print, but that makes sense. Return statements can only start with return, also makes sense. But look, for instance, simple statements that can be a lot of things can start with all of these words. So if I know that I have one of these words, then I know that it can be a simple statement. But if I have, for instance, the word, for is not here, so it cannot be a simple statement. So that's interesting. That is called the first set. So let's go back to our little story with Gukesh and myself. So it turns out that Gukesh, apart from being, the release manager and being a very serious person, as you can see for the image, he's always like very serious. He talked me in that Facebook office about the following. He is also the creator of a formatter. Maybe you know it. It's the black formatter. It's quite popular these days. And Gukesh had a problem, which is that there was some part of some programs that the black formatter was struggling with, right? And he knew that I was very interested on parsers, so he was asking me if we could change the Python grammar just slightly to allow black to format a bit better some specific code. So let's go into detail about what code I'm talking about. So this is an import statement, right? So this is importing things, and you are naming it foo. So for instance, I'm saying for my module import foo, so you import my module and you call it foo. So this is kind of cool. You can also change the name. So for instance, if you don't want to name foo, you can also say, well, I'm going to call this like different, right? Well, this is a bit stupid. Maybe I should review my slides before coming here. But let's imagine that it says bar or something like that, right? Of course, you can also like change the name there and call it the foo, right? So that's a way you rename things. Cool. The problem is that you can import many things. So for instance, you can say, for my module, I'm going to import these 3 things. And of course, Python allows you to also rename every one of those. So I can just say, okay, so from foo, I will import foo as the foo, bar as the bar. As you can see, like it doesn't fit anymore, right? Because now the line is very long. And we need a formatter. And what the formatter will do, it will use the power of parentheses, and it will rearrange everyone on their line. It's fantastic, right? It's very cool. It will also add this like nice trailing comma that you absolutely want, even if there is no next element. Why? Because if you're changing, and you're adding a new element to the list, if you have a trailing comma, you don't need to change that line, so it's not going to show in your diff in Git, and everybody will be happy. Of course, now, this has also another advantage, which is that if the lines are very long, so for instance, the name of the module for whatever reason is very long because someone comes from Java or something, then having everyone on their own line is quite useful because lines have 80 characters or even more if you have one of these super long screens. Those people are dangerous. So you have one of those long screens. So having everyone on their own line is good. Like imagine having this thing on a single line is not a good idea, right? But the good thing about Python, and this is another thing that makes Python Python, is that it just makes sense because if you just know this rule, then it works everywhere. Look, do you have a very long list? So it also works. You can also put every element on their own line. You don't need to put like the list on the same line. Makes sense. You don't have a list, you have a dictionary. It also makes sense, right? Like you can put every item on the thing on the same line. Do you have, for instance, a tuple? Well, obviously it works the same as a list. But what about a function call? It's the same. You put the arguments on the same line. What if you are defining the function? Well, exactly the same thing. You put every single argument on the same line, right? So everything makes sense. So the same way you have this, there is some structure that is very similar to these import statements, right? Like everyone on the same line, which is a context manager. So since Python 3.5, you can have context managers, and context managers, they allow you to put many things. So if you want to do it, you will put with, and then you open parentheses, and then you put like every single item, and it looks fantastic, right? Well, except that actually doesn't work because that is illegal, and that is how it makes you feel. But now you know that this is called the south face, by the way. It's one of the things that people criticize a lot about the black formatter because black formatter puts this part on its own line, and it looks like a south face, so people don't like it. Anyway, so it turns out that this is the problem that Gukesh was having, that everything else works except context managers. So you couldn't format context managers one line at a time. You needed to put the big, ugly line, or you need to hack around it, putting like continuation lines, those ugly, like, backlashes. And Gukesh asked me, like, can we change the grammar slightly so we can allow, to change those context managers when it's online, so the black formatter can do it. But it's not only about black, right? It's about everything, because this is what makes Python Python. Like, if you can do this thing on all these things, people expect to be able to do it in the other thing. It's very annoying when it doesn't work, because this is the power of what makes it very intuitive. Like, for instance, you learn about lists, sets, and dictionaries, and then now you learn about list comprehensions, and by the power of your imagination, now you have dict comprehensions and set comprehensions just by changing the character, right? It just works. It does what you expect. But this didn't. And it turns out that this, is a very complicated problem. And one of the important parts here that makes this idea of like it just makes sense is that there is a lot of complexity behind it. Because even if this should just work, it turns out that the technicalities of the grammar make it not work just out of the box. And for that, there is this sentence that I really like to mention on language design, which is a sentence by Ovid, which is I think it's either a Greek or a Roman poet, which is ars est clare artem, which basically is translated as it is true art to conceal the art, which means that basically something artistic needs to hide the way is achieved. You can still enjoy a painting if you know how it was painted, but if you focus too much on technique, you're not going to enjoy what the painter is trying to tell you, right? And this is a bit of the course of like the people that are making languages, that we don't see the language anymore. We see how it's made, right? Like it's like almost seeing through the matrix, right? You see the C code that is lying underneath. Some people tell this about magicians, right? If the magicians know the secret, so they cannot enjoy magic anymore, because every time they see another magician, they are trying to find the secret just to copy it or something like that. So there is this poetic justice. When you know how to present something beautiful to people, you lose the ability to enjoy it yourself, right? Wow, philosophy. Cool. So it turns out that this was a hard problem, but it's our job as language designers to just make it make sense. And for that, we make some big changes on the language. Turns out that apart from this problem, there is more problems. For instance, that grammar didn't actually match the Python language. For example, if you learn about the walrus operator, which is this like colon equals, turns out that if you try to do that on the old grammar, it doesn't really work, because this is the rule that is written, and this rule, if you look at the first sets of this part and this part, they are the same. So you have one of these tokens called name, which is any variable. The parser doesn't know if it's this one or this one, so this couldn't really be parsed. We needed to hack it around and write it like this, which is like not really good, because this is more generic. This will allow you to write things like 3 equals 4. And that's not good, right? Because 3 is obviously not equals 4. You cannot assign 4 to 3. But then there is this stage later in the C code when we say, well, if this is like not what we expect, then raise this error and say, cannot assign to expressions, which is really bad, because like we have this cool file with the grammar that I told you that describes what Python is, but turns out that we need to hack around it, because like this LL1 grammar doesn't really describe what Python is, then it's not really serving its purpose, right? We need to hack around. We cannot write this nice with the statements, as I told you before, because these are not valid with the old grammar. And well, if you actually look at the file, it used to be quite ugly. Like for instance, this is the rule for function definitions. Good luck changing that. I had to do that for introducing the positional only arguments, and it took me 1 day. It's not good, right? Like it's very difficult to read. So that was another problem that we had. And there is more problems. For instance, like we need to write like expressions like addition in this way, which is a bit bad, because this expression generates this tree, and then when you need to fit this tree to the compiler, you need to translate it into this other tree here, which means that you don't need to understand why, but what you need to understand is this one is not the same as this one, and there is some magical computer science that you need to do to transform one into the other. Maybe you hire a bunch of like people doing interview questions and lead code, and they will tell you how to do it. But it's not. It takes time, and it's not good. And if you have plenty of these, then you need to like pass through this middle tree called the context syntax tree, which also takes memory. Nobody like that. So what we did is that we, like Wiedemann Rosen, Lisandros Nikolaos, and myself, we created PEP 617, and then we substitute the whole Python parser by a new PEG parser. which uses different technology. Going back to the idea of the ship, if you look at the dates, so this is the original revision of Python when the first parser was introduced, and this is the commit that when we introduced the back parser. So if you look at the dates over there, it turns out that this is 30 years of difference, right? Like so they all, like this is when we change the parser, right? So if Python is our ship, we are changing something on the ship, in this case the parser, and this is a piece of Python that was there for 30 years, right? So this LL1 technology is really, it was really old, but you know, it served us well. 30 years, you know, it's quite like a good amount of time. Like if you are writing code and the code survives 30 years, you can certainly be proud. I will be afraid that my code is surviving 30 years, to be honest. But you know, I don't wish anything to the maintainers in 30 years of my code. But this is quite a long time, right? And now the question that a lot of people had in mind is that, okay, now you are substituting this super core part of the language that is making Python Python, because you know it's very simple and I can parse it just reading the next token and all of these things. And you're introducing this new super fancy parser that is going to, you know, allow a lot of super scary things. So a lot of people were scared if with this change, Python is still going to be Python, right? Because this allows a bunch of weird things. And what I'm going to show you is that yes, but also no. So the new parser, basically, I'm not going into detail, but the difference is that the old one, if you have plenty of alternatives, it uses all this math and computer science to know which of the alternatives you have in a rule is the correct one, in this case, D. The PEG parser is a bit more easy because what it's doing is that it's basically trying each rule in a time, and the first one that succeeds is the one that you're going to pick. So it's conceptually it's quite simple. So it's going to try A, then B, then C, then D. If D works, then that's the one is going to work. And the idea is that every one of these non-terminals in the grammar is a little function, which basically looks like this. So you have three possibilities in a rule. What this thing in a parser generates is basically three conditionals. So it's going to parse the first one. It's going to say, is an assignment? No. So, okay, so try expression. Is an expression? No. Okay, try if statement. If a statement, yes. Okay, return if statement. If it's none of them, it's going to return none. Interestingly, this makes the parser extremely complicated, but it also makes it run in exponential time. If someone remembers their computer science, that means it's very bad. So we use memoization. It's a very clever technique describing a bunch of research papers, very modern, because these PEG parsers are quite recent. And it basically translates those exponential times into linear times. The cool thing about context-free grammars is that you have this problem about, like, they are very powerful, but then you have this problem of ambiguity. That was the reason we couldn't introduce these context managers with different lines, because it's ambiguous in the grammar. But the cool thing about PEG parsers is because they are trying basically one rule at a time, they make them not ambiguous, because the first rule that works is the first that is working, even if several of them will work, which basically translates to they are really powerful, but also have something called infinite backtracking, which is a feature because you want this. It means that they can try infinite amount of things. That's kind of cool. But if you if you make mistakes, you need to pay them very expensive. For instance, this is in valid Python, but there was this bug when if you try to parse this, so I'm saying Python -C to just execute this, which again is invalid, but Python takes 2 seconds to know that this is invalid. Well, you would say, well, I have 2 seconds. But if you do this, it takes over an hour. Well, that was a bug. It's a bug that I fixed. But the problem is that you need to be, with great power, something. So you need to be very careful, because once you have this extreme nuclear machine of a parser, you need to be very careful. Otherwise, people will take a lot of time to just know that they wrote invalid Python. So can you imagine waiting 2 hours? Like, oh, wow, this is going to be great, and then syntax error, not great. But we fix all these bugs, and we have now these cool parsers. But now people were afraid, and now are you going to destroy Python? Well, I mean, no. We still, Python is still ruled by the Steering Council, so we take a lot of care ensuring that all of these things work. But the new parser allows a bunch of things that weren't possible before. For instance, it allows us to do new changes on the grammar much easier without impacting users. When we introduce async and await, and we make async and await keywords, this change broke everyone doing that. Like if you have async equal 3, we broke you, because now when async is a keyword, you cannot assign to a keyword. The same thing with await. If you are trying to assign to await, which used to be a valid word before, when we make it a keyword, we broke all the code that looked like that. And that is kind of not good. So we introduced the idea of having two kind of keywords. One of them is called hard keywords, which are the ones that you can assign to. But the new parser allows us to introduce this idea of like soft keywords, which are keywords that sometimes you can assign to and sometimes you cannot, which makes like all this code work again, because you can now just say like, async equals something, and instead of having this, invalid syntax, the like soft keywords will allow you to assign to async. And the first time we introduced one of these was with PEC 637, this one, called structural pattern matching. And we introduced 3 of them. If you have never looked at this, it allows you to write code like this. It's extremely powerful. Some people call it a superpower switch statement, and all of them are wrong, because like switch statements in C only allow you to switch from integers, by the way, or enums, and match statements allow you to match on really complex structures. So if you think this is a switch statement, look again. So in this case, you have match. Match is the new keyword, and then you have case, and that is the second keyword. But you can still assign to match and case. You can say like, match equals 3, and that code will still work because now we make it a soft keyword by the power of the new parser. And I'm not going to go into detail, but like this is super powerful. It's one of the things that we introduce in Python 3.10, and it makes writing some very ugly code that needs to ensure that like you're matching on the structure of different objects quite easier. So you can have here, for instance, some command, and then you split it. It's going to give you a list, and then you're going to say, well, if it's a list with one element called quit, then do this thing. Same for look, but you can go things like, okay, if the first word is go, and then there is something, capture that something, and then I'm going to use it in the expression. So, and then you can do even more things. So you, for instance, you can say, okay, I'm going to, like check on the word quit, or like the word go and something, but you can also say the word drop and many somethings, and I'm going to capture those somethings, and you can use it in the case. And also we introduced this like underscore. Underscore turns out that it's also a soft keyword now. Even if you could use it for other cases. This is the default. So this case underscore means like anything that is not one of the previous ones. But technically underscore is also a soft keyword. So the more you know. And you can do a bunch of funky things. So for instance, you can have even a class and say, well, if the user is giving me one of these click objects, capture the position in variables, and then you use them inside. So it's quite complicated, but it's also super, super powerful. And we are super, we're waiting until everyone moves to Python 3.10, because obviously people are not still using Python 3.10 massively. The world is still running on 3.8 and 3.9. But match statements were only possible due to the PEG parser. And this is even more things that you can do with dictionaries. So obviously you can have a dictionary here, and then you can match of the contents on the dictionary. So again, very powerful. But it was not possible before. But now we could make this change without breaking anyone, thanks to the power of the parser. So you see, because this is only possible with this new thing, this is what I mean with like you need to make sure that these pieces fit together. Because from your point of view, you get what you want, which is that you still use your keywords, match and case and whatnot. You're not broken. You can enjoy this new thing. And but all of this is possible because we changed this fundamental part of the language. And yes, it can be misused to convert Python into Java if you want, but also it can be used for the good. And like for the good in the sense that for you as a user, you still see the final product as Python, or some people will do it. And when I say some people, it's because some features are a bit like controversial. For instance, typing is something a bit controversial these days. And this also changes the vision of Python. Like depending on how you use typing, you may think that Python is one thing or the other. And it turns out that typing has kind of 2 words these days. One of them is the word of static typing. That was the kind of like, the way we introduced typing at the first time. So you do these type annotations, and then you run a tool like MyPy, and MyPy will tell you like, hey, you told me that this function was going to take a float, and then you're passing a string. Bad boy. And that's the usage that most people thought. But turns out that, probably most of you know, like, Fast API and Pydantic and all of that stuff. Turns out that a lot of people started to use typing in different ways, which is dynamic typing. So dynamic typing is when you're running Python, Python is reading those annotations that you place in the code, and it's using them for things that only happen when it's running. So you don't run, a program over your source code, but when Python is running, it generates these things, right? Pydantic uses dynamic typing for validation. So it just checks that when you're passing a float to the function, at runtime it's going to check that indeed that object is a float. And turns out that, depending on the camp that you are, or you can be in both, obviously, you will see Python in two different ways, right? And those ways were a bit incompatible. So we originally introduced PEP 484 that introduced the typing language, but it was thought as a like a static typing kind of thing. But it turns out that had a bunch of hacks in the way we introduced them. So we introduced them PEP 563 that introduced this from future import annotations. And this was because if you are in this world and then you're trying to use Python typing, there were a bunch of cases that didn't work, particularly when you have a class that uses something that is going to define later, and that thing defined later is using something that it was defined before, this kind of like cycle. So that didn't work. So we introduced this from future import annotations, but it turns out that this PEP broke everyone that was, well, it was going to break everyone that was going to use dynamic typing. So that was not good. So we had to introduce this new PEP, which is a proposal, which is a way to make both things work. And this is PEP 649. And the idea is that this is very important because for different people, like this PEP was not needed because they don't care about the dynamic typing cases. But as you can imagine, a lot of people did. So this is a PEP that we accepted last year. It still is to be implemented. So nobody implemented really or enforced this one. I mean, you can do from future import annotations. That is still there. But we, like PEP 563 was saying that that should be the default in the future. So we didn't make it the default. We are trying to fix the whole situation so it works for everyone. What I'm trying to say with this is that depending on the kind of user of Python that you are, you may care about one of these things or some other things, but it's our job as people making the language to ensure that it works well with everyone. And this is a very complicated case because like making sure that both cases work correctly in the face of these funky cases is a bit complicated. The way basically this PEP works is using descriptors. So when you have like this kind of like code that is using there a type that is also defined later, we kind of inject the annotations in the middle in some way. So this used to be the way the previous code was doing it, and now we need to do it a bit more complicated. You don't need to understand anything. You just need to know that there's more letters in the second slide, so it looks more complicated. So the new PEP basically injects things in a way that makes it work, but it puts a lot of complexity into the language. It's complexity that you don't see, but it's complexity that we need to take. And the purpose of taking this complexity is that you, at the end, can enjoy Python as a nice language. I'm going to skip a bit just to not complicate over here. But the idea is that there is two main uses. There is the people that if you're a small project and you are teaching Python, you may not care about code annotations at all. But if you are an enterprise user or you work in very large projects, you know that these annotations are very useful because this allows your IDE like Visual Studio Code or PyCharm or whatever to tell you like this is the function that you want, so you can click and it will yell at you when you don't pass the correct thing, and you can click and it will to the function, so it's quite useful. And what I'm trying to show with these to you is that these two use cases are totally valid. And depending on how you use Python, you may see Python one way or the other. So when we add types to the language, some people say, oh, this is not Python anymore, this looks like C++, blah, blah, blah. And a lot of people that are on the second camp, they say, oh, but we want even more typing because typing this function is very hard, and we want even more crazy syntax. And these people are kind of like opposed to each other, and it's our job to ensure that we put enough things to make everyone happy. But this basically goes into a reflection that what is Python depends a lot on how you're using Python. And in what cases you will think that some features are good, and in some cases you will think that some features are bad. But Python at the end is everything, and that's very important to have in mind. By the way, we accepted PEP 649. It's just that it still needs to be implemented, so that will probably land in 3.13. And another big change that is coming, by the way, is this idea of the global interpreted log, which is interesting. This is a big change, and this is something that has been there forever. So the global interpreted log is this big lock that protects Python and ensures that only one thread at a time can be executed in Python code, right? So if you don't know it, now you know. Everybody hates it, and this basically means that you're running your big HTTP server with a lot of threads. Well, surprise, only one of those threads can actually do things at a time, which is not super bad, but it's kind of like suboptimal. But that was there for a long time and people accepted it. But very recently, there was this gentleman called Sam Gross in 2021 that actually he was at Meta, and he actually saw us a proof of concept with a lot of crazy computer science that was able to remove the GIL without making Python super slow. That happened in 2021, and he was started in Python 3.11 at the time, not 3.12, but well, anyway. And we actually thought, oh, this is very interesting, but you need to formalize all of these things. As you can see, it took him 2 years to formalize it. He created PEP 603. And then he started the discussion. This discussion, as you can imagine, is enormous because a change this big to remove the global interpreter lock is something almost as big as Python 2.2.3, right? Because to make this thing work really nicely without breaking everyone, you need to be extremely careful. And the discussion was long. I will spare you all the topics in the discussion. But the interesting part is that on July this year, we accepted PEP 703. So this is happening actually. I can promise you. The problem is that it's going to happen in a very tricky way because we don't want to break people and we don't want another Python 2.2.3 situation. So we have this specific rollout to make sure that we know what we're doing and everything is taken care of. And this has a lot of challenges. And the problem is that you will say, well, removing no-GIL is kind of cool, because now you can execute parallel Python, but it has a bunch of problems. For instance, it's more difficult to maintain, as you can imagine, because this is a lot of complex code and makes our life as maintainers of the language much harder. It's also very, it's a problem of compatibility because it turns out that if you're maintaining C extensions like NumPy or Pandas or TensorFlow or something like that, you need to change them. They need to be able to work with multiple threads because before you have this big lock that is protecting you, but now you don't have it. So they need to change all that code, which is a problem. There's a problem of performance as well because even if no-GIL allows you to be parallel in multiple threads, it may make single thread slower. So maybe you're not using threads, you don't want your programs to run slower as well. So we need to ensure that that also works. And it's also a problem of packaging because now for a while you will probably need to package your application for no-GIL and for GIL, which basically ensures that if you're a library maintainer, you need to publish double stuff, right? And your CI is going to be double, and everything is going to be double, and PyPI is going to have double wheels, and nobody likes that. But for instance, there's good things. You have this code over here, with this code calculates Fibonacci numbers, so, your computer science 101, and then you spawn 8 threads that is calculating Fibonacci numbers. Well, if you call the version with GIL 100% of the time, so imagine that this is 1 minute, the version with no GIL takes it's 5% of that time, so it's really, really fast. This is 25 as fast as the first version if you're using 8 threads. So 25 is faster, with 20 threads, sorry, not 8 threads. This means that it scales linearly. So no-GIL does what you expect. If you have, you need to do 20 times the same job and then you use 20 threads in parallel, well, it takes the same thing as 1 thread. Because before it takes 20 times faster because only 1 thread can do a Fibonacci number at a time. And this means that it's going to be still a bit complicated because there is 2 kinds of programs, right? There is IO-bounded code that still is fine. You're running your HTTP server, it still works even if you have the GIL. And this is because, at the end of the day, you're not really doing a lot of code execution. You are basically waiting for the kernel to have some data ready on the socket. So that mostly works fine these days. But then on the other hand, there is the CPU-bounded code. So this is your heavy calculations, machine learning and whatever. And this is code that will not be able to run parallel without the GIL. The problem is that most of the programs in reality are in a mixed world when they have some I/O, some calculations, and making sure that these ones over here they're still as fast as I told you with this small example, but are also not breaking and not making it slower. The part that is just looking for I/O is complicated. So for ensuring that this doesn't happen, we made this plan. So for the first 3 years, this is going to be experimental. So we are going to do experimental builds. This means that it's not going to be official. So you can still use it. You can probably download it, and people maybe will make it available to you, but it's not official, which means that if it breaks, it's not our problem. So the idea here is that we are still going to gather information. We are going to understand the problems that people are facing. Maybe the people that are making NumPy or TensorFlow are telling us, this is very complicated, please make it simpler. So in these 3 years, we are planning trying to gather like, all this information. After 3 years, if everything goes well, because we can just roll it back, we will start shipping supported builds, which means that you will be able to download no-guilds from python.org, and we will call it supported, which means that you have problems with this and breaks in production. We will try to fix it in new versions, but it still will not be the default. So the default Python will still be no-guild. And at some point, after 5 years, if we are confident enough that we understand all the problems and we have everything under control, we switch the default to be no-guild. So the only Python that will be after 5 years is the no-guild version of Python, and everyone will be running Python without no-guild. And at every point in this journey, we can decide that this was a really bad idea and roll it back. So in case it doesn't work, right? And this may look a lot of time. You may say, I want no-guild now, but do you want Python 2.2.3 again? Probably not, right? So we are taking this with a lot of care and with a lot of possibility on going back. And this has a lot of like challenges for extensions, because NumPy and pandas and all that stuff, because it makes like you need to protect the global state that you have. Debugging with the no-guild is harder because like you have multiple threads changing data. So when you have errors, the error normally happened 3 hours ago. So you need these reverse debuggers. So it's quite complicated. But the idea is that we are going to see how people take this and how people modify these extensions, because at the end of the day, again, what we want is that in 5 years, when you open NumPy and you do from NumPy, import NumPy as MP and NumPy something, so that still works the same. So you still look at that code and say, this is still Python, and not something new that is now much more complicated, right? And this close kind of the journey, right? So this is the idea of the ship. So as you can see, there is many ways you can look at the problem, right? Like what makes Python Python? Is it the grammar? Well, yes, it's the grammar, but it's also more things, right? Because like we saw that even like things that people will say, oh, you're changing like some fundamental part of the language, so you're changing a lot of the ship. Still, like, it's a good change because it allows you to do things that I would like those multi-line context managers, right? I will feel that is Python, but turns out that the previous grammar was not allowing that. So maybe the grammar is not really what makes Python Python, because we was getting a bit in the way. But as you can see, there is other cases like the annotations story, right? So depending if you are one of the people that don't care about annotations at all, because they are teaching Python and they are kind of in the way and they're a bit more verbose, then Python is something different for you. And as you can see here, we are facing now some big change, like making Python free-threaded, which is the no-guild story. And we still want Python to feel Python after such a big change, right? And that is another turn that you can take. And that doesn't have anything to do with the grammar. It's just the runtime. So what I'm trying to say is that to answer this question, basically you need to think about what makes Python Python for you. And this is a question that only makes sense on your head, right? And as we change Python, you probably need to also change with Python. You probably are not the same programmer that you were when you started coding at the beginning, right? And then you're probably seeing Python in a different way if you started doing web applications and now you're doing machine learning. But at the core, one thing that I'm going to tell you for sure is that in the core team, we are making a lot of effort to ensure that the ship that is Python, that as you can see is very huge, still feels like Python for everyone. And that is a hard thing. But turns out that you don't need to slaughter any Minotaur to do it. You can just contribute in the open source. And this is everything I have for you. This is all the philosophy. So I hope that you enjoy the talk. And thank you very much for listening to me.